Well, thank you for being here, but thanks for Fernando for inviting me. Also, it's really a great honor. And actually, I realized looking at the conference, I might be the only one speaking really about purely complex Riemannian geometry. So I'll make also some kind of general philosophical statement about the whole subject. And actually, of course, it's particularly, I mean, even moving in some sense doing it here, because I mean this subject basically was born, I think, in these fields. I mean, not historically, Kaehler was not here, but Bochner, Andre Weil, Calabi, Lefschetz, I mean all the founding fathers of Kaehler geometry were actually here, and Kodaira, for example, I mean, just to name the few. So the whole thing about the seminar will be to tell you about new constructions of new manifolds which we can prove to admit a metric of constant scalar curvature, and to show you many examples of manifolds which do not admit metrics of constant scalar curvature in the Kaehler class, with the Kaehler restriction. So before doing that, just because of what I said, let me quickly remind you. So Kaehler metrics, I mean, for those of you who have never seen, nothing to be scared about. These are just Riemannian metrics on, actually for most of my talk, my manifold will be compact. Actually, at the end, there will be a section on non-compact, on affine varieties, but I mean, this is a compact manifold. And I usually, as we often do, we equip it with a complex structure, and we indicate by a tensor indicating the rotation by I on the tangent plane. So of course, Kaehler metrics means just that the rotation, I mean, the multiplication by I on the tangent space is an isometry. So and that would make the metric Hermitian in the language. But on top of that, every time something like this happens, you actually associate to a metric another object, which is a skew symmetric instead of being symmetric, which is a two form. And you require, the Kaehler condition is actually requiring that this form is closed, so it's a symplectic form. So in particular, I mean, among Riemannian, I mean, in Riemannian geometry, they are special for many reasons. One of the reasons actually is written right here from the beginning, because Riemannian Kaehler metrics identify cohomology classes immediately, which is something, so it's kind of a topological constraint. So, and in fact, you will see, I will almost never write the metric as the symmetric tensor G, but I will always refer it to the associated two form omega, as it's always done. Okay, so omega, of course, will represent a cohomology class, a real cohomology class here. The other special things about Kaehler metrics is actually that every tensor PDE system you write, I mean, we are going to write down Einstein equations, Riemann tensor constants, I mean, all these kind of PDE type of systems, they reduce to scalar systems immediately, because precisely, again, it's an immediate byproduct of this condition, because it's very natural. Once this is given, once you fix a cohomology class, then you try to look for constant scalar curvature, Einstein, whatever, symmetric metrics, in a given cohomology class. But then by the Didi-bar de Poincaré, Didi-bar lemma, anything representing the same class, if you pick another one, another representative, this will differ by anything else by I Didi-bar of a function phi. So, and then you can just write down Ricci, Riemann, scalar, whatever, in terms of a single function. So every even plausibly tensor problem in Kaehler geometry boils down to a scalar problem. Okay, that's a great simplification. Actually, I was lucky enough to hear Calabi speaking about the history of Kaehler geometry, and he was not shy to say that actually this was actually one of the main reasons. I mean, this simplification was actually one of the main reasons at the beginning to do Kaehler geometry. Then later it was clear why this was an important subject by itself. I mean, you can actually do computations more easily than in classical Riemannian geometry. So why? So before, as I said, I'm mid of making general introduction to the subject, so I'll be very quick. But as I said, I'm going to show you new examples of manifolds which have constant scalar curvature, and new manifolds which do not have constant scalar curvature. So why should this be interesting? So very quickly, this is almost offensive for this audience, so I will take really a few seconds. I mean, of course, what we do in Riemannian geometry, I mean, the dream is, of course, to equip any manifold with a canonical metric, the best metric, okay? So we are seeking for the best metric, and we know how the story goes in Riemannian geometry. So, of course, if you impose the Riemann tensor to be constant, then, of course, you have Cartan's classifications of symmetric spaces. If you impose on top of that the Kaehler condition, of course, you reduce the number. Then you go, and then you say, okay, so this is not good for the dream because too few examples of manifolds like this. So you start saying, well, but what about if I relax it to sectional, and then you have Riemann's theorem. And Riemann's theorem tells you, again, there are very few examples. In fact, only quotients of the three canonical models. And then in the Kaehler situation, similar situation happens. So then you go down to Ricci, and then you say, well, what does it mean to have constant Ricci? Constant Ricci is the Einstein equation. So how many Einstein manifolds do we know? Well, that's, of course, a huge problem. We don't know how many, but certainly few. I mean, there are clearly many obstructions known, and we do not expect many to exist. But if you impose the Kaehler condition on top of that, then you realize immediately there are extremely few, because even topologically there is an immediate, for example, the functional class has to have a sign, which is highly a non-generic condition on the algebraic manifolds. So you go in Riemannian geometry, of course, the next step is to go down to scalar curvature, and then here there is the kind of the bomb of the, so the Yamabe problem was asking whether any manifold admit a conform, starting from any metric, you can conformally change it to a constant scalar curvature metric. And actually the answer by Shane's theorem, we know it's yes. In fact, in some sense, now here, the dichotomy becomes almost orthogonal, because here, if you go on here, we all know the problem becomes that there are too many. Because of the flexibility of Shane's theorem is that, so which sign can you impose, for example, which is the Yamabe constant of the manifold and so on. While on the Kaehler column, the problem is that there is actually absolutely no way to have a Yamabe type theorem on this side, because we've known, I think, since the 50s and the 60s, I think Lichnerowitz, Matsushima knew, and but then came the work of Futaki, who found a very clear and neat obstruction to the existence problem for constant scalar curvature metric in a given Kaehler class. So where is this obstruction and what does it say? Actually, seems it is a remarkably simple idea. So the idea is to take on a manifold, take X, a holomorphic vector field, you have your Riemannian metric, and you build a number in the following way. Let me see if I can use the pointer. So you take the scalar curvature of your metric, and you just normalize it. You remove the mean in such a way that this is the Laplacian of something. This function h is known to be the Ricci potential of the manifold, okay? So once the scalar curvature essentially is the Laplacian of something, you take this Ricci potential, and you see how holomorphic vector fields act on it, okay, just by differentiation, and you integrate over the manifold. So why this number should be interesting, I'll show, comments in a second, because actually a bit more than 20 years later, there was a major reformulation of this number due to Donaldson at the beginning of the millennium, actually. We actually extended this obstruction to a much wider range of manifolds, in fact, not even manifolds. You can define this thing on a variety or even on a scheme, and you replace, of course, on such singular objects, you have to be careful what is a holomorphic vector field. Actually, you substitute the data of a holomorphic vector field with a one-parameter subgroup of the automorphism with a given polarization, linearization. And then you go and check two numbers, basically. And this is really a very beautiful interpretation of this Riemannian object, because so once you have a polarization, you look not just at the algebraic numbers associated to this specific polarization, but you have to go and look to all powers, tensor powers of this polarization. And you expand, for example, let's take the simplest one. You take the space of holomorphic sections of this polarization to every power, and you see the asymptotic behavior in the power. Okay, this by standard theorems, Grothendieck, Riemann, Roch, and so on. You know it's a polynomial of this type with some coefficients. You do the same thing for what is called the weight of the action. So you go to the top wedge product of the space of holomorphic sections of the polarization, and again you go and see how the action behaves under the power, the tensor power of the polarization. Again, there's kind of a similar version of the Grothendieck-Riemann rock that tells you that now this is the polynomial you are looking at as m goes to infinity. I mean, this is the expansion as the power goes to infinity. And then, remarkably, Donaldson proved that this combination of the coefficients, in fact, of the first 4 coefficients, gives actually something that once the one parameter subgroup was actually the one induced by a holomorphic vector field and everything else makes sense, this is exactly the Futaki invariant. This number is called the Futaki invariant of the manifold with this scalar metric. So this is a kind of a subtle theorem, of course, but actually if you believe the equivalence of this, so for more than 20 years up to this interpretation, I think everybody in the subject agreed there was an easy and a difficult fact about this number. The easy fact is that if G is of constant scalar curvature, then this number is 0. Well, this is obvious because if S of G is constant, then of course by removing the mean you're getting 0, so you take the Ricci potential is 0, you're integrating 0. Okay, so that's the easy thing. And then there was always a subtle thing that actually this number does not depend on the metric G, but it depends only on the Kaehler class of the metric. Okay? Now, if you believe the equivalence, of course, I'm pushing the difficulty somewhere else, but if you believe the equivalence, actually in Donaldson, if you take this formula here, it is exactly the opposite. Because the fact that this number does not depend on the metric is obvious because actually there is no metric here. Okay? There is just the polarization L, which is the Kaehler class. Okay? The C1 of L. While, of course, if you look at this formula, what becomes difficult is to show that this number is meaningful in terms of metrics of constant scalar curvature. Okay, so why this should be 0 if there is a metric of constant scalar curvature? These are just algebraic numbers associated to your algebraic manifold. Okay, so but this is the story. And now the point is that, of course, people have been trying to develop techniques to compute this number for many classes of algebraic varieties, and we will see actually that's part of my talk too. So, but in general, it's not difficult to show that there are plenty of examples where this number is non-zero. So this number, I mean, and as soon as this number is non-zero, that Kaehler class cannot have a constant scalar curvature representative for sure. Okay.
These numbers, have they some nature? Are they rational, for instance?
Not that I know. No. So this what this means is that if you go back to the column of the dream, no, at the place of the constant scalar curvature Kaehler, we cannot say okay any Kaehler manifold. A theorem like any Kaehler manifold as a constant scalar curvature metric is completely wrong. Okay, so Calabi himself in the 80s proposed another, I mean a more general class of metrics. And now this makes sense only in complex geometry, and then he called them extremal. So actually the simplest point of view was to look at critical point of functionals over the space of Riemannian metrics. Now this object here is just the space of the metrics in a given Kaehler class. So capital omega is the cohomology class that I'm fixing. Okay? And now I move the metric inside here. I don't move the metric in the space of the whole space of Riemannian metrics. So this is the classical Hilbert functional, but it's very clear that in Kaehler geometry the Hilbert functional is completely useless because if you integrate the scalar curvature, you get a topological number. Okay, so it's constant, whatever. This is completely independent of which representative you take of this class. Okay, so he proposed to look at the L2 norm or the square of the L2 norm of the scalar curvature, just by arguing by simplicity. And now this is a very interesting Euler-Lagrange equation. And in fact, I didn't write it down because I want to jump quickly to the core of my talk. But I mean, the point is a metric will be a critical point of this functional if and only if the scalar curvature has this very peculiar property. Oh, maybe I can even add the definition of the diesis, the del diesis. So this is a typical operation in complex geometry. You take a function. So this is a real valued function. Basically, you take the 1-0 part of the gradient. So the gradient is a vector field. It's a real vector field on your manifold. But if you have a complex structure, real vector field split into 1, 0, and 0, 1. This is just like saying instead of using x, y coordinates, you take z and z bar coordinates. Okay, so you look at the z part. So that's the dièse. The dièse is the sharp operator. Okay, so a metric is extremal. It's a critical point if and only if the scalar curvature itself produces a holomorphic vector field by this operation. Now, this is a really beautiful interaction between complex and Riemannian, but still, the big question here is, of course, if the metric is constant scalar curvature, this is of course extremal because this is the zero holomorphic vector field. So this is clearly a generalization of the previous one, but still, it's very hard to construct non-constant scalar curvature extremal metrics. Okay, there were a few examples, actually some built by physicists for reasons. Okay, so this was the end of the introduction, kind of, and these are I mean, I'm going to give you kind of a geodesics among, don't worry, it's going to finish at 5. I mean, it's, it's not going to describe all this. So, in general, there is a kind of a very general framework to attack the problem. I will be specific about the extremal equation and the constant scalar curvature equation, but actually there is no need for the general construction. So the general construction for producing this type of metrics comes from the following idea, which is by no means mine. So suppose that instead of having, I mean, you want to construct a smooth object with a given metric, special metric. Okay, suppose that by accident you have a singular object with the same type of metric. And here by singular I will always mean, unfortunately, in this talk, isolated singular points. Okay, I mean, whether we can do something similar for higher dimensional singularities, that would be a huge step forward. Okay, and actually at the moment I will also assume, but this is not strictly necessary in some sense, that actually these points are even quotient singularities. Okay, so what you see here is a group, gamma. So this is a point, and associated to a point is a group. So locally the manifold is Cn modulo gamma. Okay, so this you have to believe. Sometimes by accident you have a singular object which solves your problem. Can you go back to smooth out of this? And the idea is very simple. Suppose that actually locally you can actually resolve this type of singularity. So I take one of each these corners, and I assume that there exists actually one model, smooth model, sitting on top of it, with a Kaehler metric, so a Kaehler resolution of this singularity, where now the Kaehler metric has to satisfy many properties, actually 3. First of all, it has to be Kaehler. Reminding, not every complex singularity has a Kaehler resolution, so this is already a restriction. And in terms of the metric has to be asymptotically locally Euclidean. So that means that if I go sufficiently far away in Cn, or the pullback of the inverse image of Pn in X, I need to regain the Euclidean metric, or actually the quotient of the Euclidean metric. This will be cons at infinity. This will look like Cn mod gamma at infinity. Okay. Plus, I want them to be solutions of some problem. Now, in my case, I want them to be scalar flat, okay? Because now there's a general ansatz saying how these metrics look like. If you have something like this, actually this metric has to be dd bar. I mean, it's actually given by the Kaehler potential. It has a very specific form. The fact that it starts with x squared over 2 is the translation of the ALE condition. Because if you take dd bar of x squared, you get the Euclidean metric. So the leading term has to be the Euclidean metric. And then decaying term, some errors. Now the scalar flat equation imposes the powers. I mean, this is a PDE, so the solutions to the PDE has to be special, and it's special in this sense. So it has to go like this. Actually, it will be clear why in a couple of slides. But just one comment, because now these coefficients turn out to be important. Oh, sorry, among them, you should have in mind that the main source of examples also historically of this kind of objects are the Ricci flat examples. I mean, of course, Ricci flat beats scalar flat. And they have been by far the most important class of examples of this kind of things. But of course, there are plenty more. Now, in particular, this coefficient turned out to be very important in this kind of story, because this is actually, you can prove that this is what is the ADM mass of the manifold, okay? So in the case of Ricci flat, of course, you would call these objects gravitational instantons, and they were being studied by physicists for other reasons, okay? And that's the ADM mass, but actually this would be 0 if Ricci is equal to 0. So Ricci 0 implies that the mass is 0. Okay, so that's that will be important for later. But okay, so this is kind of these are a number of local assumptions on the type of singularities we have. So remember, we have this kind of strange monsters with corners, which solves the problem, plus locally a solution of this type to the problem. So then, of course, the obvious idea is to glue them together. So remove a little corner around the singular points and try to insert a rescaled version of these models down at the right size. Okay, so of course now so this, and actually the fact that we are doing this explains why scalar flat. So for example, if this was constant scalar curvature 20, of course you might have guessed, okay, let's look for local models of scalar curvature 20. So why 0? Well, 0 because 0 is the only number which stays bounded under scaling. Okay, so I prefer to have control on the scalar curvature, even if it's the wrong scalar curvature, than actually putting the right scalar curvature right from the beginning. Okay, so anyway, it's clear that in this way you construct an approximate solution to your problem, and then the question boils down to whether, so okay, in this way you have constructed now a smooth manifold with a Kaehler class, with a canonical representative of this Kaehler class, which of course is not still the solution of this problem, but then the question is whether you can deform this approximate solution to an actual solution. So as I said, I don't want any credit for this because actually it's older than me, this idea. So this was invented by the physicists at the time where nobody knew how to produce even one Calabi-Yau. Now we know Calabi-Yau manifolds. But for the Ricci flat Kaehler equation, for many years, the mystery was whether they existed. Okay, so this construction was the proposal by the Cambridge School to actually produce examples of Calabi-Yau manifolds in the 70s. So in fact, and this also tells you also a little bit of the philosophy here. So why do you have a non-trivial example where to start from? Well, take the trivial torus, a flat torus, but now you can quotient it by some kind of, for example, x in minus x. This is the most famous quotient. This gives you a few singular points. And this is still flat, so you might say, okay, but this is still, okay, you pass from trivial easy to trivial difficult. Good. So now what? But now you apply this machine, you resolve these singularities with this trick, and actually what you have constructed is a genuinely smooth manifold, so it has to be a K3 surface by classification theory, okay? And you have also some kind of idea of what the metric should look like. So this was the first. Of course, physicists basically told people what I wrote there. I mean, then the actual proof that this actually gives a Calabi-Yau manifold came in 1993, okay? So, but that was much more than enough for people believing that actually Calabi-Yau metrics existed, not just flat ones, okay? Okay, so, and again, this you might know this story also for another reason, because it's the same idea that Joyce used to produce the first examples of compact manifolds of special holonomy. Okay, in that case, he took the 7 torus, you quotient by some action, group action, and then again, it's an orbifold, which is flat, but then again, you can resolve it. So what's new here is to apply to another system of equations, not the idea itself. Now, okay, here I prefer to be a bit quick at this point because all this, I mean, of course, among possible singularities of the form Cn mod gamma, there is actually the smooth situation. So when gamma is the trivial group, so actually it's a kind of a strange type of singularity. And in this situation, of course, what we would be describing is the standard blow up of a smooth point. Okay? So that's why, I mean, the resolution of singularities and blow ups look similar. They are just using a different model. Okay? So of course, for the resolution of singularity, you generally have to resolve the singularity. If you're taking a smooth point on a smooth manifold, you have to take the blow up of Cn at the origin and construct a specific metric on that. Okay. Now, and actually, but this part of the story is kind of old, and what we did with Frank Packard and Michael Singer in various papers a few years ago. Okay. So here in this talk, I will go directly to the non-trivial situation of actually singular points. Now, this I prefer not to comment, but I need to tell you. So strange enough, the extremal equation, which looks much more complicated than the constant scalar curvature equation, I just remind you, the extremal equation is the del sharp of the scalar curvature is a holomorphic vector field. Okay, so that looks, in fact, it is a higher order equation. In fact, maybe for purely analytical you will see kind of the equation soon. But if you write down, of course, what are we going to do? Whether we start from the approximate solution or from anything else. I mean, we fix omega, and we want to find phi such that omega plus IDD bar phi solves, for example, scalar curvature equal to 0 or to 1. This turns out to be a fourth order equation in phi. Okay? Remember, it's a second order on the coefficients of the metrics, but the metrics are second order in the phi. So it's a fourth order equation, nonlinear equation in the phi. Now, if we also impose the extremal equation, it's even worse, because that means that del sharp of this is holomorphic, which is another equation. So it's a sixth order equation in phi. Okay. So why should the extremal equation be even attackable? The point is, actually, yes, there is an algebraic trick for which the extremal equation works, but I don't want to describe it. The whole point is to make sure that holomorphic vector fields actually behave well under resolution of singularities. At least here you will see it one way. Because remember this principle I mentioned to you, every problem in Kaehler geometry has to become a scalar problem. Well, that's clearly true for everything except for the vector field. I mean, a vector field is a vector field. There's nothing you can do about that, unless it's Hamiltonian. Okay, if it's Hamiltonian, it is given by the derivative of a function. Okay, and then you can look at the Hamiltonian potential of this function. Now, the trick here is to use Hamiltonian potentials of that, but you have to prove that the resolutions of singularities actually preserve the Hamiltonian properties. Okay, so once you solve this technical problem, also the extremal problem becomes a scalar problem, and you can work on that. Okay, so resolutions of singularities work well, and this is actually expected. I mean, now I don't want to comment too much, but it's expected because the extremal equation has the beautiful property of being open. This was proved by Lebrun-Simanka. I mean, in the Kaehler cone, this has to be an open set. So this kind of is a generalization passing from singular to smooth of the Lebrun-Simanka theorem. But let me comment. So this is just a recap of the notations. So we have a compact m-dimensional constant scalar curvature orbifold, isolated singularities, and these are just the names of the objects which are coming in. Oh, okay, so this was, this is a side comment for those who know. I mean, there are the two main reasons why people like me are studying this kind of problems is, one is the dream. No? Okay, you want to associate to every manifold a canonical metric. But once the dream is established, or at least to the extent to the dream to be established, what do you do with these metrics? And the general dream, there's a second order dream. I mean, once you have slept the first time, you sleep another time, and you dream of doing with this type of metrics what people have been doing for more than 100 years on Riemann surfaces with constant Gauss curvature metrics. Okay, so you want to construct. Basically, the idea is to construct moduli spaces of algebraic varieties with from the metric point of view, exactly as Teichmüller did for Riemann surfaces, okay? So, and in particular, this should give us light and, I mean, many, in fact, in this case, it would be even new results. I mean, once you have this, you can construct a kind of a Weil-Peterson metric, you can compactify spaces and so on. There is this whole world behind this story. And to make this dream some kind of mathematical foundations, people have invented the notion of stability of corresponding manifold, which is called K-stability. And there is a big, huge conjecture. Clearly, by far, the most important problem in Kaehler geometry is to prove that something has a constant scalar curvature metric if and only if it's stable in the corresponding sense, because this would be the major step in this kind of second dream, okay, to produce. I mean, if you think of, in the situation of Riemann surfaces, it's a beautiful piece of history of mathematics. I mean, because it's kind of, you pass from the Poincaré metric on the disk to the Riemann surface, to Teichmüller, to the compactifications of Teichmüller, Abikoff, Beers, and so on. And then you want to compare it with people in next room did, actually next room here, Deligne, Manford, and so on. So at the end, you end up looking at the same class of objects, but two different compactifications, and then we all know how beautiful is the story of comparing them, okay? So this is actually the beginning of the same story. I mean, at least for the type of manifolds which we can prove admit a constant scalar curvature, or a Claire-Einstein, or an extremal, or, I mean, a canonical metric, okay? So this is just a slide saying, okay, for this type of manifolds, so the manifolds that you can actually obtain by resolutions of singularities, with this very with these Kaehler classes, with these polarizations which are actually close to the boundary of the Kaehler cone, okay, then this kind of stability works, okay? But as I said, this would be a completely different. Okay, so now I have my equation, constant scalar curvature. I know that the solution cannot be, while for the extremal case, actually the theorem was going to tell me you can do whatever you want, okay? Basically, you start from an extremal orbifold, you resolve singularities, you have an extremal manifold. That's it. Now we know that this theorem is false if you substitute extremal with constant scalar curvature, because there is Futaki invariant. Okay, the Futaki invariant is there and is going to tell me no. You start with a constant scalar curvature orbifold, you resolve the singularities, and there are two possibilities. Either by a miracle, the Futaki invariant of any resolution is 0, or there is an obstruction, okay? So, and in fact, there is an obstruction, and we need to understand it. This is the moment to go back a little bit to the PDE side of the story. So, okay, instead of phi on the slides, I used f. I start with a metric. I deform the metric with a function, f. And I look at the scalar curvature operator, and I expand it, of course. I suppose that f is sufficiently small in some norm, so, and of course the scalar curvature of omega plus I d bar f will look like scalar curvature of omega plus a linear part plus a nonlinear part. Okay, the linear part, which is actually what is governing 90% of the problem, looks like this. I mean, and this gives you a little bit of the feeling of the problem. So this is the B Laplacian of the function plus rho is the Ricci curvature of omega, a scalar product in the sense of 1-1 form. This is a 1-1 form against the 1-1 form given by dd bar phi. So this is fourth order plus second order. Actually, this formula is true only if omega is of constant scalar curvature. Otherwise, there would be also an extra term of first order. Okay, but I've skipped it. I mean, and actually, when I started thinking about this, I said, okay, if the linearized operator is this, of course, the point is, can you tell me something about the kernel and the image of the linearization of your equation? You look at the shape of the operator and you change problem, because, but fortunately, Lichnerowitz and Matsushima, again, thought about this for a long time. And actually, they were able to actually completely characterize the kernel of this operator in a very beautiful geometric form. So something is in the kernel of this operator if and only if you produce a vector, a complex vector field by the standard operation I described you, then this becomes holomorphic. So this would be the, so or vice versa. If you take a Hamiltonian holomorphic vector field, if you take the Hamiltonian potential, this automatically becomes an element of the kernel of this operator. So this has a very beautiful geometric interpretation. So if you give me a manifold, at least with a little bit of luck, I should be able to tell you immediately how big is the space of, how big is this kernel, okay? So let me give me a name to these functions, the very special function. Of course, there will be always one, because this will be the one giving me the zero vector field. And then, in general, there will be other elements of the kernel. So then, here I'm going to skip all the technical points, but you can imagine how the strategy of the proof works. I constructed by a picture an approximate solution to the problem. I look at the linearization of the problem. And now the question is whether I can deform the approximate solution back to an actual solution. And this is done by gluing theorems, so implicit function theorems of different forms. This is actually what we did with Frank Packard for the blow-up, and a similar machinery works in many situations. And here I'm highlighting the situation where the old machinery doesn't work. And it's the case where you are resolving singularities where you want to glue in a model which has zero ADM mass. This is by far the most difficult situation. It takes many, many pages to check all the estimates for the operators involved, because this pushes all the problems to kind of a next step. I mean, if you remember the expansion of the metric, it's x squared plus e times x to the 4 minus 2n. Oh, actually, maybe I can also make a comment about this expansion here. When I gave you the interpretation, when I gave you the by this formula, this actually essentially proves why you have this x squared plus x to the 4 minus 2n. These are the elements of the, these are the green functions of the B Laplacian. Okay, so they have to behave like this. Okay, so anyway, this is, so the strategy is now to deform back the thing, and the zero mass situation for the models, which is geometrically one of the most interesting ones. It's not just because of pleasure of completeness. Remember, this is the situation, for example, where the resolution is Ricci flat, which is by far the most interesting case for physicists, for example, okay? Is this gravitational instant. So can you insert a Ricci flat model inside something? So you have to use this kind of thing. And actually, if you do the analysis of the PDE, so you have kernel. The point is that here you have some kernel to control. And the point is, the implicit function theorem, of course, will force you to work orthogonally to this kernel. And orthogonally to this kernel will translate into the fact that you are going to be able to solve the problem if some condition is satisfied. I mean, all this is, as I think, at least both me and Frank, that's the way we came into this subject, because if you think of the beautiful situation of minimal surfaces, of constant mean curvature surface in Euclidean space, this is exactly the same situation. When you want to glue, for example, something to, and you have this balancing, we call them, in fact, balancing condition, because there are global conditions that you have to satisfy in order to be able to do these things. And this is a kind of a translation of the fact that you have to work always orthogonally to the kernel. Okay? Now, in this situation, these conditions look like this. So what are they asking me? You take the Hamiltonian potentials of the holomorphic vector fields, and you compute something like the Laplacian of them plus the scalar curvature. This is a constant, remember. It's the starting constant of the base orbifold plus phi, and you compute it at the singular point that you are resolving. Basically, you build a matrix, and you want to know whether this matrix has maximal rank, and if this kind of orthogonality condition is satisfied, then you can actually prove that the classes you have constructed, or something nearby, actually do have a metric of constant scalar curvature. So this is from a purely PDE point of view. You brute force analyze the equation, and you see it. Now, the problem is we knew there was an obstruction, and the PDE gave us this obstruction. So the obvious conjecture is this obstruction the Futaki invariant? Is this saying the Futaki invariant of the resolution is equal to 0 or not, or it is different. So we had to compute it. Computing the Futaki invariant. Computing the Futaki invariant is never fun, but at the beginning there is a moment of real happiness. Remember, the key property of the Futaki invariant is that it does not depend on the metric, but it depends on the Kaehler class of the metric. Okay, so basically this means you are free to choose the metric you like in that Kaehler class to compute the Futaki invariant. Because you see, if the point is, okay, give me the constant scalar curvature metric and make a computation, the problem is that we are not able to write down any metric of that form. Not even, I mean, we are still an explicit metric, constant scalar curvature, or whatever, we are absolutely not able to write it down. So the point is, by using the cohomological invariance of the Futaki invariant, we can actually write down the metric we like and do the computation. That's the moment of, so let me skip the technicality. So now what do? There is this parameter epsilon moving around. So epsilon is what? Epsilon is essentially the size. On one hand, so remember you had this orbifold with many corners. You had to decide which size. I mean, you remove a ball, let's say, of radius epsilon on one side, and you are inserting something like epsilon squared eta on a model on x eta here on the other side. But this, of course, will be truncated of somewhere, at distance 1 over epsilon to the alpha. Okay, and then there is this parameter epsilon in this gluing construction. So here, the point is to expand all the objects in epsilon and to see what's going on. Okay, and the first thing you have to expand is actually these functions in the kernel of the operator, of the linearized operator, so the Hamiltonian potentials of the holomorphic vector. So first you need to have a nice correspondence between holomorphic vector fields and Hamiltonian holomorphic vector fields, and then you need to understand a little bit how the Hamiltonians behave under this construction and how they vary by epsilon. Once you are there, what are we really doing? So we have the resolved manifold with an approximate metric, approximate solution. And the question, we would like to know what is the Futaki invariant of this scalar class with respect for this holomorphic vector field. But at the same time, we can push down the vector field. Now we know it's still Hamiltonian, and we have this relationship about the potentials. So we also have the Futaki invariant downstairs of the orbifold. Now, of course, you can ask the question in general. So what is the relationship between these two? And this is what we achieved in this formula here. So this, of course, we are expanding in epsilon. Epsilon equal to 0 is the singular situation. So it has to start with Futaki, then plus some power, times basically the value of the Hamiltonian potential of the vector field at the point minus its mean, times this object here, minus this combination instead. Now it's Laplacian plus, and you can see this is exactly the same formula we got from the PDE side. Okay. Now, but here also it's important to understand these are cohomological numbers. You can write them. This is the Ricci curvature of the model, and this is the Kaehler form eta on the model with compact support. So you can actually write down what these objects are. And now we are assuming S, the scalar curvature, is equal to 0. These are completely general, but if you also impose S equal to 0, you are left again with the ADM mass. So the mass of the model is coming into this expansion, okay, here. Well, and also here, but in this form, okay. There is a combination of the first two terms of the expansion of the metric. Okay, so that means actually that our balancing PDE type balancing conditions are exactly the first order term in the expansion of the Futaki invariance. Okay, so then it's okay, then it's done. I mean, that means that these two things agree, and then this gives two proofs of the same thing on one side, because now I can use a theorem which says by Calabi, which says that if I have an extremal metric in a class which has 0 Futaki invariant, it is actually constant scalar curvature. Okay? So since the extremal problem is never obstructed, I can resolve, put the extremal metric, I do the computation of the Futaki invariant. If I get 0, I solve the constant scalar curvature equation even without noticing it. Okay? That's one way. So this reproves, in some sense, the same theorem. But actually, this also shows that this is almost an if and only if. I mean, so if these conditions are not satisfied, then there is no, because this is really the Futaki invariant, so there is no constant scalar curvature matrix in these classes. Okay. Yeah, so okay, so new proofs, non-existence results. I mean, this I just rewrote. I mean, if these conditions are not satisfied, then actually the problem was not solvable. Okay. There is an obvious objection that we did to ourselves. If this is the type of things you have to, if I give you a constant scalar curvature orbifold, and I ask you to compute this, of course, this is a hopeless task. Because of what I said, we are almost never able to write down the metric. So you can imagine, even if I'm able to compute the automorphism group, which implies I know what are the holomorphic vector fields, I certainly will not be able to find explicitly the Hamiltonian potential, because I need the metric, and I don't have the metric. So you can imagine, I cannot do any of these operations really in practice. I know they are doable, but I cannot do them. Okay, so is this just philosophy? Well, go back to the beginning of the story. When does this story really gives, for example, in the Calabi-Yau case, when it was applied to the flat torus, when Joyce applied to the special holonomic to the flat torus. So you start with if you start from a kind of a trivial example, then hopefully you can do computations. But now in this situation, what does it mean trivial? Well, this is the trivial I could get. So, well, actually, the whole problem is more interesting in positive scalar curvature. This is something I should have said. All these problems are by far more interesting in the positive scalar curvature case, because that's the situation where you expect to have continuous symmetries, holomorphic vector fields. So that's, in some sense, it's the most difficult, and so it's the most interesting. Okay. So, for example, if you take P1 cross P1, you can easily write down actions for which the quotients have 4 singular points. The quotient is clearly Keller-Einstein, so in particular it's constant scalar curvature, it's orbifold. You can actually decide even which kind of algebraic variety it is. It's easy. I mean, you write it down. It's the intersection of 2 singular quadrics. Okay. So, So you actually go and check, and here in this situation, because P1, of course, is one of the few situations where you can actually write down the metric. It's the 2 sphere, it's the round sphere. So you write down the metric, you do all this computation, Laplacian of phi, blah, 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 and you check that the conditions are satisfied, for example. So this gives a resolution of this object. This gives resolutions of these objects for which there is a constant scalar curvature metric in the appropriate classes. And you can start playing. Of course, once you get involved in computation, it's actually fun. But I mean, okay, just another example. Take P2, and now you quotient by Z3, acting by cubic roots of unity, 3 singular points. Actually, I'm bypassing completely. There is a problem. You also have to show that these singular points, you have a local model with the scalar flat metric ALE on the local model of this. So for this, we are in dimension 2, and fortunately there are beautiful theorems by Cronheimer for SU2, the gravitational instance of Cronheimer, and then plus Calderbank-Singer and Vyaklowski for any cyclic group, and for actually any group, okay? Any U2 finite subgroup. Okay, so here we have no problems. This is a singular cubic, if you write down what kind of algebraic variety it is, and the output is that these are balanced, so you can actually resolve these singularities by keeping constant scalar curvature. Maybe you know the other side of the story. There is another type of deformations. This is a comment for, so for example, this singular cubic is also the limit of Keller-Einstein manifolds on another side. If I deform the complex structure to make it smooth, So this is in the boundary of the moduli space of smooth cubics, of course. So, and smooth cubics have Kaehler-Einstein metrics. So this is actually the limit of canonical metrics in two ways. Kaehler-Einstein on one side, if I keep the Kaehler class and I move the complex structure, but also ours, constant scalar curvature, by changing the Kaehler class and keeping the complex structure fixed. Okay, you can, as I said, you can play as much as you want. This is a 3-dimensional, but actually it's easy to write down 2-dimensional examples, and then when you go to higher dimension, you start getting very frustrated because you cannot, I mean, it's become harder and harder to find. I had to rely on the help of friends, and actually there's a group of people in England running a database of Fano manifolds, fortunately. So I asked them for help because you really need a computer to find a Kaehler-Einstein threefold with isolated singularities. You see, now as soon as you grow, the point I want to make, I want to criticize my theorem in some sense. The assumption of the fact that we are working on isolated singularities is almost okay in dimension 2. When you go into dimension 3, it's a disaster. I mean, the typical singularity will be much more complicated than an isolated orbifold singularity, okay? So you really have to work with a computer to find them. There are, I think, if I remember well, 14 Kaehler-Einstein toric manifolds, and some of them, I mean, and you can apply. So in fact, just one comment on that side. Of course, a major step forward in all this program would be to extend all these theorems to higher dimensional objects. So instead of singular points, in fact, even to blow up of a point, blowing up some manifold, this has been done by Zeghelidi and Seiladi, for example. That's a beautiful, but the analog resolution of singularity theorem is still missing for higher dimensional singularities. And now, I would like, in the last 5 minutes, to describe to you a variation of this idea, much more directed to Riemannian geometry, because, okay, this is more directed maybe to algebraic geometry. So now, I will start assuming that the manifold is not compact. So, and in fact, my manifold itself now will be one of the models that I used in this construction. So these models are non-compact manifolds. I don't know which sides. I'm trying to maximize the number of people who can actually see. But you're very symmetric, so. So now my manifold M becomes what before was actually the model, x eta. Okay, so, and now x eta, and actually typically, this is not just my fault. I did it for a few years, but it's also in books by, I mean, we always draw these things like this, like an ALE scalar flat space, Kaehler, of course, but actually, since I'm going to speak about the ADM mass, this is, of course, for you, many of you will be reminiscent of Penrose type inequalities and so on. This picture is wrong. I mean, this suggests the existence of a stable minimal hypersurface here, which is actually not there. But okay, the picture is already passed into history. So really, the right picture, I think, should look much more like this. Okay, there is no special submanifold. There is no neck in these things. Okay. Now, okay, but anyway, that's it. I cannot change everything. So I actually just realized it. I mean, you can, as far as I know, nobody has computed the mean curvature of the rotational invariant hypersurface, for example, and just to realize that there is nothing interesting happening. I mean, anyway, so now this becomes my base manifold, and whether actually it could have singularities and apply the resolution of singularities. But let's say we want to just blow up smooth points. Now I pick up, and I asking myself, can I produce another manifold? So now the blow up at P of the manifold, well, now it's M of X is the same thing. And I want to produce another metric in all my talk it has been omega, so omega epsilon, where again the scalar curvature of omega epsilon is equal to 0. Okay. Now, you might say, well, this is more difficult because it's non-compact. We have the theory. Well, actually, this is easier. I mean, because it's easier thanks to Hartog's theorem. Because if you remember, the abstraction is the Hamiltonian holomorphic vector fields, blah, blah, blah. Now, okay, on these spaces, they cannot exist. So this is even though this is non-compact, thanks to Hartog's, this is kind of the non-obstructed situation in the compact story. So what I'm saying is that proving this theorem, it's very easy. But now I want to refine this information. I don't just want to know whether such a metric exists, but I want to know some Riemannian properties of this metric. And remember, all these theorems are based on implicit function theorem. So this exists for epsilon less than some epsilon naught. Okay, so there is a small value. This epsilon actually corresponds to the volume of the exceptional divisors that you are putting here. So it's like you are bubbling. Okay, you are creating a bubble, and you can prove there are small bubbles. Okay. Now, what is the effect? I mean, what is the? Okay, so this is just saying, okay, the blowing up theorem works. There is no, it's the easy situation. But that's what I said. But I want to understand how is this construction changing the ADM mass of these objects. Now, here, and in particular, I said, I mean, the kind of one motivating question, but actually the question is interesting by its own means. So whether, remember I told you Ricci flat implies zero mass. So obvious conjecture, is it true the converse? I mean, does zero mass implies Ricci flat? And here, some very sporadic examples were known of the fact that the answer to this question is no. So there are scalar flat objects which are not Ricci flat and still have zero mass. And actually, Hein-Lebrun especially built kind of a general theory for the relationship between mass and Kaehler metrics. So this is the prototype examples were known. So okay, this is the manifold itself, the total space of this line bundle over CP1, and they show that there are, if you blow up points put in a specific position, then actually you can preserve the zero scalar curvature condition and put the mass to be zero. But actually this type of examples is a byproduct of a very elegant formula for the mass for this type of objects, which is proved by Hein and Lebrun. So they proved that actually in this specific, in the Kaehler case and in the ALE Kaehler case, the mass is a cohomological number. Okay, so I will always assume that the scalar curvature is zero, so forget the second term. This integrates to zero because it is zero. So it's left really with the Furniture class against omega to the n minus 1 renormalized in a suitable form. So this means this is very useful, of course, because if now you ask me which is the mass of this new thing, I can apply that formula. It's very easy to compute the Furniture class of the blow-up and so on. All these are very classical. And what you get is that the mass of the blow-up with the omega epsilon is the old one, essentially. Okay, now there will be normalizations mistakes, but that's the point is that plus epsilon. Okay, so plus essentially the volume of the exceptional divisor that you have put into the manifold itself. It's increasing by this amount. So how much can it increase? Well, it can increase at most by this mysterious number epsilon bar, which is hidden in the implicit function theorem that is giving you the gluing theorem. So final thing, actually, we are not able to say if you blow up one point how big it is, but with Karen Corrales, what we did was to prove that once you do it once and you get this number that I will start seeing how it depends on P, I can blow up, if I blow up another point Q sufficiently far away, then, Of course, it has again a constant scalar curvature method. I can repeat the argument for the existence, but the mass of the blow up in 2 points, well, not the map. Now it's epsilon. The epsilon bar for the 2 points is actually greater than or equal to the epsilon bar p minus 1 over d, where d is the distance from Q to a kind of the compact core. Okay, it's a kind of a quantitative version in this specific case of the implicit function theorem for this. And basically the outshot is that basically now if you give me a model, and this is really the end, if you give me a model which has negative mass, any model with negative mass, I can blow up some points. I mean, there exist points. They must be sufficiently far away in order to apply this argument. But there are a number of points, a finite number of points, that if I blow up, I turn the mass to 0. I pass from negative to, I increase by something, and I can control how much. So if the distance between these points is sufficiently big, it will go to, I can make it 0, for example. I can actually make it even a bit positive if I want. Okay, so that was the, unfortunately, the statement is not very friendly, but that's the moral is on the blackboard. Okay, so in some sense, this gives a dual to Hein-Lebrun. No? Hein-Lebrun said there are very specific examples where actually the symmetries of the game allows you to pick few points, but they have to be very special. So, and you have to start from some very special model. So this is kind of the dual. Start from whatever you want. Actually, negative mass is the generic situation here. And blow up many points, but as long as they are far apart. Okay, so this is kind of prescribing the bubbles of these equations in order to make the mass 0. That's it, I think. Thank you.